Today we will start our chapter number 9 on the magnetic properties of solids. We have already studied the dielectric and the optical properties of solids. The electrical properties were also studied before. Now we are going to discuss the magnetic properties of solids, which are very fascinating and has several applications of solids. So the magnetic properties of matter have fascinated physicists, chemists and engineers for many years. In recent times, these properties have been the subject of special interest because of the information they yield about the constitution of matter and the interactions involved therein. This information, being truly interdisciplinary, is of interest not only to physicists but also to other scientists and engineers. Magnetic materials have wide-ranging technical applications, from transformer cores in electrical machinery to magnetic tapes in computers. Now in this chapter we shall discuss the magnetic behavior of three independent atoms. So we will start from the magnetism of individual atom, and then the magnetic properties of conduction electrons in ordinary metals, and we will discuss various classifications of solids with reference to magnetic properties, that is diamagnetic solids, paramagnetic solids and ferromagnetic solids. So let us now discuss the basic concept and the basic formulas. Now, just like the dielectric moment, we are defining the magnetic moment of a magnetic dipole. So if you have a magnetic dipole having a positive magnetic charge on one side and negative magnetic charge on the other side, and they are displaced at a distance d, then the magnetic moment mu m is defined as the magnetic charge, one of the magnetic charges multiplied by the distance. Now here I have shown this magnetic dipole. You can see that if you have an externally applied magnetic field, then this magnetic moment of magnetic dipole will interact with this external magnetic field and will generate a force, a magnetic force in the dipole. And just like the electrical dipole, in the electric field having an electric force, we are using the same formula to find the magnetic force, which is Qm into B. Okay. This is the next page. So when there is a magnetic force and the magnetic dipole is fixed, say, at its center, then this force will act on the positive magnetic pole in one side and on the negative magnetic pole in the other side, and therefore it will produce a torque. And this torque is defined as the magnetic dipole moment, the cross product of the magnetic dipole moment and the magnetic field. So the effect of this torque is to turn the dipole and align it with the field in a manner similar to the way an electric field aligns an electric dipole. So because of this torque, the dipole will possess an orientational potential energy given by the formula V is equal to minus mu m dot V. So this is the dot product. It is the same formula we used for the electrical potential energy of an electric dipole in an electric field. So equation 9.4 gives us the magnetic potential energy, and here if theta is the angle between the field and the dipole direction, the minimum energy will be minus mu m into B, and this will occur when theta is 0, that is when the dipole lies along the field. And the maximum energy is achieved at theta is equal to phi, where the dipole is oriented opposite to the field. Okay, now here we have used hypothetical magnetic charges just to match with the electric charges. But in magnetism this is not so. The magnetic charges do not exist, and it is actually the north and the south pole which are always associated with a magnetic dipole. So magnetic north and south poles are actually the reality. So we have defined the magnetic dipole in terms of magnetic charges, but such charges do not in fact exist. All the known magnetic properties of matter are attributed to the rotation of electric charges. We recall from the elementary physics that an electric current fluid acts like a magnetic dipole of moment. So this is the basic generation of the magnetism, that whenever there is an electric field in a loop, it generates magnetism such that we have a north side on one side of this loop and south side on the other side of this loop. So because magnetism is also due to the motion of electric charges, so we got to have this north and south side exist in pair, and we cannot separate these two poles. So here equation 9.5 redefines the magnetic moment as equal to I into A, where I is the circulating current in the loop and A is the area of the loop. And the direction of mu m, which is a vector, is always normal to the plane of the loop, and such that the current flows counterclockwise relative to an observer standing along mu m. So is that if you put the thumb in the direction of the So if you curl your fingers in the direction of the conventional current, so thumb will give you the direction of the magnetic moment. So figure 9.2 shows the magnetic dipole moment associated with the current loop. I represents electric current and vector L is the angular momentum of electron producing the current. Okay, the current loop in an atom are composed of rotating electrons. In this case, we can establish a simple relation between μm and the angular momentum L of the electron. Noting that the current is E into omega over 2 pi A area of the loop is equal to pi r square, and the angular momentum is given by, for a rotational motion, is given by m r square omega, where omega is the angular velocity, and we can now use equation 9.5 to write the magnetic moment, which comes out to be minus E over 2m into L, by substituting the value of the current I and the area of the loop A in equation 9.5. So we get equation 9.6. So note that there is a negative sign here, and this negative sign means that the magnetic moment is always opposite to the magnetic dipole moment, is always opposite to the magnetic moment L. And this coefficient minus E over 2m is called the gyromagnetic ratio. So the gyromagnetic ratio is defined in this equation, and it is equal to minus E over 2m for the revolutionary motion of electrons moving around the nucleus. Usefulness of equation 9.6 derives from the fact that it expresses μm in terms of L, which is a familiar quantity in quantum mechanics. So L will be quantum mechanical operator. So this equation gives us a relationship between the magnetic moment and the magnetic dipole moment and the magnetic moment. In addition to its orbital motion, the electrons also rotate about its own axis, and this rotation of electron also produces magnetism. This magnetism is called the spin magnetism. Thus there is a magnetic moment associated with this spin, and this moment may be related to the spin angular momentum S. And this relation comes out to be μm is equal to minus E over m into S. So this magnetic moment is due to the spin motion. The spin angular momentum is S, which shows that the spin gyromagnetic ratio is minus E over 2m. So this is twice the value obtained for the orbital motion. And we have, so you must note that the gyromagnetic ratio of the spin motion is always double, is always twice than that of the gyromagnetic ratio of the orbital motion. So the classical derivation of this ratio does not apply to the spin motion because this motion is entirely quantum in nature. Okay, let us now think about the dynamics of a classical delta in a magnetic field. This figure shown here in the question 9.3 is in fact the precessional motion. Why do we have a precessional motion? That follows